Good morning, good afternoon, good evening, or good night, depending on wherever you're calling from or wherever you're watching this and listening to this from later on the on-demand mode. This is Weekly Science Review, sponsored by Vetri Labs. Here we focus on electrochemical technologies. We take a deep dive into the papers that are published in open access mode. Here at Vetri Labs, we focus on implementing electrochemical technologies at scale. Today's discussion is going to be led by Manikandan Ramani. Mani is Director of Chemical Engineering at Plug Power. Over to you, Mani.
Uh, Good morning, good afternoon, everybody. I'm just going to share my screen. Okay, can you see my screen?
Yes.
Okay, I'll go full screen here. Okay. All right, so we're going to talk about the publication. It's in Journal of Electrochemical Society in 2020, operating ethylene carbonate-based electrolytes with lithium and manganese-rich and nickel, manganese, cobalt, lithium-ion batteries. The role of oxygen release on the choice of the cyclic carbonate, and it was published by Hubert Castiger and some other folks there. Just a quick overview. This was talked about in one of the prior lectures by Chuck. There's a cathode, which is typically on the lithium-ion battery, a lot of material which actually houses the lithium source, lithium, cobalt, iron phosphate, manganese, and the material we're going to talk about today, which is the lithium manganese rich NMC cathode materials as well, cathode active materials. On the separator, typically, the separator contains the electrolyte, and there are different electrolytes of choice. Today, we're going to talk about LiPF6, and we're going to talk mostly about ethylene carbonate and fluorinated ethylene carbonate electrolyte system. Anode is typically graphite. In some cases, the anode can also contain lithium alloy metal. From a charge standpoint, the delithiation happens on the cathode, and the lithium plus goes to the anode side. And on the discharge, the lithium that's been accumulated on the anode goes back to the cathode side, just as an overview of how the lithium-ion batteries work. On this publication, they are primarily focused on the lithium manganese-rich layered oxides, which are very promising because they have a higher capacity, but they do suffer from faster fading of capacity, especially in electrolytes that contain ethylene carbonate. And this has been attributed to several mechanisms, and this publication talks about, and they deconvolute several mechanisms with several studies, and finally hone into the structure, the cathode active structure, releasing the lattice oxygen at a higher degree of which is greater than 80% SOC, or at potentials of cathode potentials greater than 4.7 volts with respect to lithium plus. It causes higher impedance and capacity fade. And they have studied fluorinated alternatives with fluorinated ethylene carbonate, and it seems to address and mitigate the mechanism associated with the lattice oxygen and reaction with electrolyte. They have further looked at separating the mechanism, again, with electrochemical mass spectrometry. They show that the electrolyte stability is not the root cause, whereas the interaction between the electrode and the electrolyte is the primary root cause. However, having said that, they believe that adding the fluorinated ethylene carbonate itself is sufficient to address the cycle life capacity fade associated with the cycle life. And next slide. Why ethylene carbonate? Again, the electrolytes contain a mixture of carbonates. Ethylene carbonate is preferred because it does form a protective layer on the graphite anode, and it stops the decomposition of the electrolyte. It prevents the self-discharge, and the solvation energy between the lithium plus and the electrolyte with the ethylene carbonate, with LiPF6, with the ethylene carbonate is favorable from a stability standpoint. So these are the main reasons why they contain the ethylene carbonate. For again, the purpose of this study is to compare electrochemical stability of the electrolyte systems in the ethylene carbonate and fluorinated electrolytes. Use in situ or online electrochemical mass spectroscopy to study the products that are seen at the higher potential during the decomposition. And then in addition, they have taken coin cells with the cathode active materials and the special electrolytes that we've discussed. They have taken those and built coin cells with them. And actually they've tried to show real life aging studies and done several tests with potentials and to deconvolute the other mechanisms as well. In terms of decoupling tests, first step that they talk about is they have found a way to address the pathway to the failure mode. The capacity fade is the main problem statement, and they look at both impedance increase and loss of lithium as the reasons for capacity fade. By running C over 10 and 1C discharge rate, they are able to, as a function of cycle life, they're able to ascertain if it is impedance rise or if it is due to active area or loss of lithium as a mechanism. For example, if the loss between the C over 10 and 1C discharge rate is constant, then it is possibly due to lithium loss or active area. If the delta keeps increasing between the C over 10 and 1C, then there is impedance to play a role in that. So that's how they separate that. And they found that impedance loss is the primary reason, impedance increase, excuse me, is the primary reason for the capacity fade mechanism. Three main buckets in terms of experimental, how they deconvolute this. One is they consider electrolyte decomposition as a primary mechanism because in the past, there were several literature that suggested that mechanism, wherein the electrolyte containing ethylene carbonate actually decomposes faster at the potentials where you're going towards the 4.5, 4.6 volts when you're charging. And electrode decomposition as well. They've considered electrode itself decomposing, and also the reaction and interaction between the electrode and the electrolyte. On the electrolyte decomposition, the experiments they've conducted, they use a separate cell with the electrochemical mass spectroscopy. And on the working electrode, they use a carbon working electrode. And they use the electrolyte system, both the ethylene carbonate and the fluorinated ethylene carbonate. And they take the working electrode to the potentials that you would typically see when you're in the first activation step of the battery, which is almost close to 4.7. And they actually take it even further to 5 volts to study if there's any difference in terms of carbon dioxide evolution between the two different electrolyte systems, the ethylene carbonate and the fluorinated ethylene carbonate. In terms of the electrode, they study that as well. In addition to that, they make coin cells and study the fluorinated ethylene carbonate versus the ethylene carbonate with NCM 622 coin cells. And in terms of the interactions, they further make coin cells and they separate them by having the ethylene carbonate ethylene carbonate coin cells and do cycling tests to study them. In the other case of the electrode decomposition, they study by doing the mass spec again and looking at the CO2 just on the, now it's attributed coming from the electrode itself. So on the coin cells, they focus the negative to positive capacity ratio. They make sure that the materials of choice, both the NCM coin cells and the lithium manganese rich NCM materials are both higher negative to positive capacity ratio. And this is chosen because they want to avoid additional failure mechanisms arising due to lithium plating. And it's a very smart way of controlling the test so that they don't have any additional side effects due to choosing the cathode to anode capacity ratios. On the anode, they choose a graphite of 8.3 milligrams per centimeter square loading. On the cathode for the NCM, it's a 10 milligrams per centimeter square for NCM. Separator electrolyte is poly PE with LePF6. And obviously, we are talking about two different electrolyte systems, EC with the DEC and FEC, fluorinated ethylene carbonate with the DEC. On the anode, for the manganese, lithium manganese rich materials, 6.7. And for the cathode, they actually have two different cathodes when they study, especially the coin cells. One is pre-activated, which we will talk about later. They actually try to degas the cathode so that they remove that oxygen that gets generated during that first activation cycle. And they build the cell subsequently into the coin cell to eliminate that source of oxygen and decomposition products that are not further available in the pre-activated cells. On the separated electrolyte, again, they stick with the similar composition as the NCM material. So the only difference here is obviously the amount of oxygen that is available between the NCM and the lithium manganese rich NCM materials. In terms of cycling test, they do a rate test first in the coin cells. They charge it at a very low current, C over 15 rates to 4.7 volts, at which obviously there is a potential of oxygen the lattice oxygen getting released because you're above the 4.5 volts with the spectral lithium plus. And then they discharge with the C over 15 rate to 2 volts, very slow discharge again. And then they do this 3 cycles at C over 10 to 4.6 volts, so they don't go to 4.7 anymore. And then they operate at C over 10, discharge to 2 volts. And then they do rate test, which is C over 0.3 C charge, and then they go to a constant voltage charging after 1 hour at constant voltage, or if the current drops to below 0.01, then they stop the charge. So all the CCCV means constant current and then switch to constant voltage mode. And then CC means constant current discharge. So they do these rate tests wherein they charge at different rates and discharge at different rates. And they almost go down to 3C, all the way from half a C to 1C to 2C to 3C, and drop it back down. And subsequently, they also change the charging rate from 0.3C to 0.7C in the process. So after the rate test is done, they do start the cycle life test, wherein they start with 3 cycles at C over 10 and C over 10 discharge, and then 30 cycles at a charge rate of 0.7C and a discharge rate of 1C. So this sequence is repeated. And for pre-activation cells that I talked about, they have a pouch cell, and they do the activation step, which is going to the 4.7 volts, which is done only once. And then they discharge, and then they degas about 4 volts at both cycles, and the electrodes now are all the decomposition products and the organic products that are formed are washed out and then made to coin cells with an expectation that they have removed any electrolyte electrode interaction products, and the coin cells, cathode and the electrolyte, do not see those products in subsequent cycle test. Sorry. Stop sharing for 1 second. Okay. This is discharge capacity, milliamp hours per gram of the material, and versus cycle. You can kind of see, this is done at 25C. You can kind of see the rate test and the cycle test. And there was repeated excursions during charging that goes up to 4.6 volts. Again, there's only one time it sees 4.7 volts, and then the rate test and the cycle life test goes only up to 4.6 volts. And in this case, the fluorinated ethylene carbonate outperforms the ethylene carbonate. The discharge capacity fade is much faster, loses about 50 to 100 milliamp hours per gram within 50 cycles, versus it is at least 2.5 times better with the fluorinated ethylene carbonate system. This is the, they further did the online electrochemical mass spectroscopy, which is, they studied the carbon dioxide evolution, and they wanted to make sure it only came from the electrolyte. So they used a carbon black working electrode, and they studied the interaction just between the ethylene carbonate and the fluorinated ethylene carbonate, and it was sealed AB cells, so they could actually extract the gases from one side of the working electrode. And they saw that the onset of the decomposition for CO2 starts at around 5 volts, or significantly takes about 5 volts. And this system, from this test, they could see that the electrochemical oxidative stability was similar between the ethylene carbonate and the fluorinated ethylene carbonate system until at least about 4.8 volts. So this could not be the mechanism for what they were seeing with the ethylene carbonate added electrolyte system, because the fluorinated ethylene carbonate and the ethylene carbonate systems decomposed similar fashion. So they concluded that this cannot be the mechanism for what they were seeing with ethylene carbonate electrolyte system. On the cycling studies, this shows, this is again, especially with the fluorinated ethylene carbonate system. And the blue dots are the pristine, and the light green are the first cycle pre-activated. As we talked about, the first cycle is where they go to 4.7 volts. And if we can remove the oxygen and we can remove the decomposition products, then we should expect better results in terms of capacity fade if we can remove them and package them into a coin cell. I'm not sure if it's a practical approach, but this at least decouples the failure mechanism, and it points us towards going towards higher potential. And it also indicates that the mechanism is related to the lattice oxygen release, or the gassing due to that. And again, due to the onset of that potential reaching 4.7 volts. And you can see that the slope of the pre-activated cells also goes down, but it is at least at a much better slope compared to where the activation was done in the coin cells, where the decomposition products and the gassing had no chance of being removed. So the gases and the decomposition product end up increasing the impedance of the cell, whereas with the pouch cells, where they could degas electrodes and wash it, obviously you can remove the impedance causing products and mechanism. That's what this shows. So I have to stop my share again. Okay. This further shows the the ethylene carbonate pre-activated degassed electrodes that were formed on the coin cells versus the fluorinated ethylene carbonate formed on the, again, pre-activated with the pouch cells, later formed on the coin cells, versus a ethylene carbonate in a coin cell without any outside pre-activation, which tells you that, again, since the products were removed in the pre-activated cells, they performed much better in the capacity fade test. And pointing towards the same mechanism should happen. Again, they did this both in the NCM and the lithium manganese-rich NCM cells as well. Again, it all comes back to the mechanism of gassing that, and then the oxygen that is produced chemically reacting, not electrochemically, but chemically reacting with the electrolyte systems. This was a charge study with electrochemical mass spec on the NCM C622 cathode material. You can see in that window of 4.1 to 4.5 volts, 4.47 volts, you just about start to see oxygen evolution at that 80% SOC around 4.5 volts. And then it goes up. The CO2 evolution starts a little earlier, actually. And the thought was it's possibly to come from the electrolyte impurities and the surface impurities of the electrode. And then the degassing, or I should say the lattice oxygen release happens after. Then it accelerates the rate of CO2 evolution as well, which then starts the mechanism that's called the rolling, they call it the rolling fade mechanism, which increases the mechanistic loss once you go to the higher and higher potential. So that's what they did with the electrochemical mass spec study. And this was just to show on a coin cell, not looking at a true cathode potential, but just going to a cell voltage of 4.6 volts versus comparing to a 4.35 volts. Both systems, again, ethylene carbonate and the fluorinated ethylene carbonate, you can see if you don't go to higher potential, you don't get into the capacity fade, which kind of clearly indicates that the degradation modes are associated with the electrode decomposition first, and then later associated with the interaction of the electrode with the electrolyte further. That's the end of discussion. Any questions?
Great. Thank you. I think we can come on video and bring slides as needed. So thank you, Mani. That was very nice summary of the paper. So if you don't mind going into the slide that showed the very first rate.
Yeah, the first charge study, the Cycle Life.
Cycle Life, yeah. I think the question that I will ask, it's all in all of those slides, but wanted to understand. See, when I believe the increased capacity that's shown is the low rate C over 10 capacity, right? The ones every
Yes.
40, 50 cycles.
Yes.
So post that, there seems to be some recovery.
Yeah, right here.
Right. So even in the blue curve,
I saw that. Yeah.
Yeah, blue curve. When you look at the blue curve, there is an increased capacity post that C over 10. Did they comment on the mechanism for why that is the case?
I don't honestly remember if
Okay.
they commented on it, but
Okay.
I have to check on it.
Sure. Yeah. So
that's interesting.
Yeah, that's an interesting one to see what's happening there. The other one, okay, if you go to the CO2 with the voltage and the oxygen evolution.
Yeah, one second. The next slide itself, I think.
Yeah, no,
yeah, I know. This one right here.
Yeah, right here. So looks like.
Sorry.
Yeah, no problem. Looks like CO2 is an early indication of what's exactly happening than oxygen. And if that's the
It's kind of
case,
interesting.
yeah,
Yeah.
if that's the case, if we they did, my question was if we had actually capped the charging voltage to 4.1, would we have seen a better cycle life?
Which they did.
They did it at 4.35.
Yeah. Oh, yeah, but they're still showing at 4.35, it's still
Right.
better, right, than 4.6 cell volt. Now, this is cell voltage. You have to probably subtract. I'm going to guess about 0.1 volts for the anode. So let's
I
say
know.
point, yeah, 4.5 probably on the cathode.
Got it. Got it. So the earlier voltage is
Okay.
potential rather than cell voltage, right? Is that
Yes. So this is actually true lithium to lithium plus.
got
So that's the difference there.
it? Okay.
Go to 4 points. Good point. I didn't quite really. I should have actually mentioned what this is in terms of lithium plus.
Right. So then it matches.
Then
So
it
yeah,
matches.
you're right. You're right. 4.35 cell voltage is definitely closer to 4.1
4.1.
versus lithium. Yeah.
Exactly. Yeah.
Yeah. Yeah. Okay. Cool. Yeah. That was nice to see. Um, these only thing is the mechanism change with the low rate. I don't know. Yeah. If
Yeah. So the CO2 starts, like to your point, because it's like chicken or egg, right? You know, the oxygen needs to come out.
right.
You need the reaction with ethylene carbonate for the impedance for the gas the degassing to happen, and then the reaction product to happen, and then the impedance to build up. So that's kind of the subsequent mechanistic steps. But then they're saying the CO2 evolution itself starts even before that.
Yeah.
So there's obviously a contribution to your surface impurities and how your quality on the electrode is and the electrolyte is. So there is some contribution just from that itself that causes the impedance rise.
Yeah.
And further, there's obviously the oxygen, the lattice oxygen release contributing further to the cascading effect of that. That actually accelerates that impedance rise as well. So there's definitely two different things. But when you line it up with the oxygen and CO2, I was at least shocked to see that didn't make sense. Why would I have CO2 before oxygen? And they do explain it away with it's possibly from the electrode, but there's really no proof. They really dug in any deeper to find a proof associated with that, that it is in fact the impurity, which I could have done by taking the NCM material, or in this case, that's what they did, took the NCM cathode material and put out the working electrode instead of the carbon in this case.
Mm-hmm.
They did a carbon when they studied the electrolyte decomposition alone. In this case, they did the same OEMS study with NCM 622 as the cathode material.
Mm-hmm.
I think they could have cleaned up. They could probably have cleaned up the impurity with the acid wash or whatever, and they could then have done another OEMS study. Then they could have possibly shown. See, now it coincides. The CO2 coincides exactly with after, or actually just after the oxygen evolution starts. Then that lined up everything.
Yeah, it's quite possible that even without impurity, that you have some CO2 formation before substantial O2 evolution.
Correct.
Right.
Exactly.
And because that will create a local mass transport issue, and then the actual polarization of the cathode will be to a higher voltage.
Exactly.
And that will
cascaded. Exactly. Yeah.
Cascade. Yeah. Great.
Yeah, so I had a question. In the conclusion, they bring up this this question that they didn't really answer. It's saying, like, why are these fluoroethylene carbonate more stable than the EC-free electrolytes? And then they provide like a couple of solutions, but they don't actually show where they got that. I was just wondering, which of these do you believe? So they say one of them is it's higher stability because like at electrochemical oxidation at higher potentials.
Okay, it's not that. Actually conclude it's not that. One thing they do is they do conclude it's not that, right? That's the I think I agree with that conclusion that it is not associated with that, but it is probably a chemical stability between oxygen ethylene carbonate versus fluorinated ethylene carbonate. So for some reason, oxygen reaction with ethylene carbonate versus a fluorinated ethylene carbonate is more inert than an ethylene carbonate. that's kind of at least a hidden conclusion there, that fluorinated ethylene carbonate is more inert to oxygen than, which kind of makes sense. Most of the fluorinated compounds are inert, more inert than non-fluorinated compounds. But that's how they don't really talk about it, but that's probably where we have to, I think, take a leap of faith on that one.
Yeah, that was their, I think, conclusion. They're like next steps, maybe. That's like what they could do in the future to like find something to back that.
Right. Yes.
And the delta in the low rate capacity versus high rate capacity compared to the two different systems, oh my God, it's a huge difference, right?
It is a huge difference.
Yeah. So if you go to the very first chart. Yeah, look at that delta, right? It's unbelievable that impedance rise.
It is. It is extremely high impedance rise.
Yeah.
I don't know if the fluorinated ethylene carbonate systems, how is their initial impedance like compared to, I mean, obviously it is good enough. I see the discharge capacity, but I don't see their initial impedance because they talk about ethylene carbonate providing you some benefits there.
Right. If they had the charge, the quote unquote efficiency, charge discharge efficiency, then we would have compared it. I think it would be equivalent. I would.
No, I think you're right. I don't have the numbers though. I don't think they have the numbers here. I didn't.
Got it.
At least they didn't plot it. They may have written it up somewhere. They didn't plot it.
Yeah.
Yeah, but I think, Chuck, your point is a good question. I don't know why this. How can this go up unless this is? I assume this is all C/10.
Right.
Did they plot this as is this C/10? I don't know.
I think the high capacity here is C/10.
Yeah.
So that's there are two things happening here, right? So when you look at the DEC without fluorination, that this indicates that there's a huge impedance loss that causes the capacity fade, number one. Mm-hmm. Number two, when you look at the fluorinated one, yes, there is some impedance loss, but part of the capacity is regained back when you do the low rate discharge and charge, right?
Yeah.
Low rate discharge. What is that healing mechanism?
Mm.
And that will tell us the exact, maybe it's the intermediates that form and that go back. So there is some reversible capacity loss and some irreversible capacity loss.
Yeah.
At least in the case of fluorinated.
Yeah. Go ahead, sorry.
No, for the non-fluorinated one, they don't have the next cycle. I don't know why.
I don't know. I think they concluded the test to be failure at 100. At least that was my presumption.
Okay.
And they probably did the subsequent test as an end of life evaluation, and then called it done. But that was, mentioned very.
Yeah, because if we had quantified what is that reversible capacity in the case of non-fluorinated, then we can see whether there was any reversible capacity at all, or if there is none, then we know that will point to different directions.
It's a good point. Very good point. Yeah. Yeah, and in some battery system I've seen it, where if you keep the voltage, if you either go to the high voltage or you stay at the low cathode potential, there is some self-healing that happens, and in a thin, or what do you call it? Length scales are much smaller in a lithium system. Mm-hmm. I used to be in a nickel metal chloride system. That was a bigger length scale. So diffusion was happening at a bigger length scale. And so when you keep the cathode at a lower potential, things equilibrate over length scale. But with lithium, it's not that much of a length scale to equilibrate. So it could just be a cleansing step that could be happening where the products are decomposed back into the electrolyte, or maybe solubility is enhanced back in the electrolyte. So you're not seeing anything built up on the electrode, maybe. Mm-hmm. But yeah, I think it was I felt like this was a very good study to decompose the electrode-electrolyte interaction but in terms of the different cycle tests, they could have provided a little bit more data and analysis, I thought.
Other questions, comments, thoughts? Okay, if not, Mani, what are we talking next week?
Oh, yes.
Yeah.
Okay. Sorry. Okay. Next week, we're talking about oxygen functionalized COP nanowires is efficient and stable electrocatalyst for OER, oxygen evolution reaction, and for full water splitting.
Great. It's a very timely paper. Everyone is interested in electrolysis and hydrogen generation. So water splitting is a very timely one. So please join us next week. If any of you would like to lead the discussion, please send us an email at info@vetrilabs.com. Thank you for joining. See you next week.